Good evening, ladies and gentlemen, and thank you for waiting. We were just trying to make sure we got as many of those that have registered for tonight's session in. I'm sure more will join as the evening progresses. You're no doubt sick of the BGs by now, so let me introduce our speakers for tonight. And firstly, apologize for Karabo, who is unfortunately doing a concrete pour and is therefore not able to be with us this evening. Our topic tonight is Off the Deep End, lessons learned from the design and construction of the Zandvliet wastewater treatment works. And I'm sure our speakers are going to be able to explain what they mean by off the deep end and why they were either in the deep end or paddling towards the deep end. The two speakers tonight are Vicky Ma, who graduated from UCT with a BSc Engineering, and her co-conspirator is Ben Pierre Gerber, or just known as Ben to his friends and his colleagues. Ben graduated with a National Diploma and then a BTEC in Civil Engineering from the Cape Peninsula University of Technology, or CPUT. Not kaput, they tell us. Ben is a registered technician with EXA and is currently undergoing his candidate technologist training. And Vicky is undergoing her candidate engineering training. Hopefully they will both achieve their professional status in due course. As you will see, once they start explaining their backgrounds, they have both worked predominantly in the water and wastewater environment. Ben's done a little bit of other stuff along the way. They both joined Oricon when they graduated, and I think Ben did his experiential there, that we now know as Zutari. So with that said, I'll leave it over to Vicky and Ben to go through their presentation, and then we will handle Q&A at the end of the session. Thank you, Vicky and Ben. Over to you.
Thank you, Tom. Thank you for the lovely introduction. Good evening, everyone. It's a pleasure to have you all here. Welcome to Off the Deep End, the lessons from the design and construction of the Zandvliet wastewater treatment works upgrade in Cape Town. As Tom has mentioned, myself, Ben Gerber, and my colleague Vicky Ma will be running you through the presentation. Hopefully you enjoy it. Hopefully there's some things you can take away from it, something that you could learn, something that you could use in your future designs. Yeah, let's get into it. Okay, so let's just firstly start off by introducing ourselves. So I am Ben Gerber. I was born in George in the Western Cape. I matriculated at Outeniqua High School in George. Moved to Cape Town after high school, obtained my Bachelor's of Technology from CPUT. I then very recently registered as a professional engineering technician in 2022. I have about 5 years of experience within the built environment unit at Zutari and Oricon. Major projects that I have been involved in, both national and international. Some that are noteworthy are the current Harbour Arch development in Cape Town, which most of you would have seen when you drive into town. They're busy with the construction and they topped out now the first tower. And then St. Mary's water treatment works in Sydney, Australia. I believe this is one of the biggest water treatment works in Sydney. Then I also assisted the Oricon Africa team in the design of the Calatrava Tower, which was planned to be the world's tallest building after the Burj Khalifa. I believe the construction of that has halted at the moment. Then something that I also found interesting at the beginning of my career was I assisted in the design and rehabilitation of the civil services after the Christchurch earthquakes in Christchurch, New Zealand, which was some offshoring work for our Oricon Australia team. Okay, then on a bit of a more personal level, I'm a very adventurous, very outdoor person that love spending time outdoors, either by the beach or the mountains. Cape Town's a perfect place to live for me. So I love surfing, I love free diving, anything by the beach, or I love the mountains for hiking, day hikes, overnight hikes, and trail running. Okay, then Vicky, over to you.
Hi everyone, my name is Vicky. I was born in Shanghai, finished my high school in Durban, and graduated from UCT in 2014. Straight after, I joined Zutari as a civil engineer in the water unit. I worked on a number of water and wastewater projects in South Africa and Africa, but the most notable being the Zandvliet wastewater treatment works. I also feel more personally tied to this project as I did my thesis on this on the site, then worked on the design of this upgrade, and now construction through. So in my spare time, I enjoy traveling, I enjoy good food, love eating. I enjoy being outdoors, hiking, or going to the beach. And my passions are architecture, fashion, and art. So let's jump into our presentation. For this presentation, we'll be telling you a little brief history of the Zandvliet wastewater treatment works, take you through the scope of works for our contract, the design assumptions and ideas that went into the design, the process of works, the construction, and also the lessons that we took away from this experience.
Okay, let's move on to the history. So before I start with the history, let me just explain and make clear the basic function of a wastewater treatment work is to remove solid waste to prevent it from reaching the environment, and as well as removing the nutrients such as nitrogen, phosphorus, and ammonia to prevent deoxygenation and eutrophication within the receiving water bodies, and to disinfect the water so that the treated effluent does not endanger human health. The process usually involves pre-treatment, primary treatment, secondary treatment, and tertiary treatment, which is now all applicable on Zandvliet wastewater treatment works after the latest upgrade. So jumping into the history of Zandvliet, construction of Zandvliet wastewater treatment works began back in 1986 and was commissioned 3 years later in 1989 to treat an average dry weather flow of 40 megaliters a day. The plant treated municipal water from the surrounding areas of Khayelitsha, Blue Downs, and Monwabisi. The flow was lifted into the inlet works by 2 screw pump stations. The inlet works then removed debris and grit from the wastewater. The screened flow then flowed by gravity to the 2 conventional activated sludge reactors, which operated under the modified Lutzig-Ettinger system that optimizes nitrogen removal. Mixed liquor from the CAS plant was then fed to the 5 secondary settling tanks, which separated clear effluent from the particular biomass by means of sedimentation. The clear effluent then drains by gravity to the chlorine contact tank, which disinfects the effluent against pathogens before it is being discharged into the Kales River. The return activated sludge from the SSTs was returned to the CAS to prevent washout of biomass. The waste activated sludge from the CAS plants were diverted to sludge lagoons. Over the years, the plant expanded to cater for the growing population. First, 2 more secondary settling tanks was added. Then the sludge lagoons were replaced by a sludge dewatering facility, which eventually had 4 belt presses. 1 more clarifier along with a scum removal system was added in 2005. In 2009, the first ever ultrafiltration membrane plant in Africa was commissioned on Zandvliet wastewater treatment works thus bringing the total capacity of the plant to an average dry weather flow of 72 megaliters a day.
So since the last upgrade in 2009, Zandvliet and the surrounding areas have grown significantly. In 2014, Zutari was appointed by the City of Cape Town to further upgrade the plant to treat an average dry weather flow of 90 megaliters per day by constructing an 18 megaliters per day ultrafiltration membrane plant. However, at the time of appointment, the plant was already receiving flows higher than 90. So the first step in the design was to make sensible projections on future flows and loads expected within the Zandvliet catchment. So we looked at the historical wastewater flow and load data recorded at the plant, as well as the population data from the national census. Next, we assessed the plant performance capacity and carried out a conditional assessment of all of the works. After our investigations, we found that the plants were hugely overloaded and that the flows were likely to immediately exceed the proposed upgrade of 90 megaliters per day, and were likely to reach 120 by 2023 and 150 by 2040. So for this upgrade, we designed the civil infrastructure for the eventual flow of an average dry weather flow of 150 megaliters per day and equipped mechanically for 90 with redundancies. We also identified a number of bottlenecks on the plants that needed immediate alleviations. So 4 different tenders were awarded to civil and to mechanical. Construction began in 2017 with structures that would alleviate the bottlenecks first, and then the whole upgrade is expected to finish next year.
Okay, then, and very interesting picture that we will show you here is this is actually a Google Earth photo of Zandvliet wastewater treatment works taken in January 2017. So this, just take a close look and see at the open fields on the right and Kailicha informal settlement on the left. Then we move on to 5 years later. This is currently about 5 months ago. This was taken in January 2022. 5 years later, you can see the massive expansion and everything that has been done over the last 5 years. Okay, then I'll jump into the process. So pre-treatment, it started at the beginning. The existing screw pump stations and inlet works, which you can see in the photos, were a huge hydraulic bottleneck. Flooding often occurred during high flows. This drowned the flumes and caused inaccurate flow readings. The inlet works was also ineffective in removing screenings and grit, which caused issues downstream. So, a new screw pump stations and new inlet works were designed to cope with the increasing flows. This new civil infrastructure design capacity was built for an average dry weather flow of 150 megaliters a day to allow for future upgrades as well. The new inlet works complex consists of a lower screw pump station, which receives all the incoming flow to Zandvliet. Rubbish is removed through a series of mechanical screens, and the grit is removed through degritters. Screenings that are removed are conveyed into a skip for off-site safe removal. One of the war stories from site, from the construction of the inlet works, can be seen in the next video. During
That's funny, that's a big fuck up.
During the construction of the deepest base on site, a flooding occurred. This was due to an open sluice gate that no one knew was open as it was submerged in water. It was fine before the excavations began, as the sand on the other side applied pressure to block the flow. But once we started to excavate, there was not enough earth to hold back the flow. Luckily for everyone, no workers were inside the excavation, as this would have been a massive health and safety risk to all involved. In the following time-lapse video, being played, you can see the flood that occurred delayed construction by approximately 5 days, but in the end, we managed to still construct a beautiful inlet works. The inlet works was the deepest building on Zandvliet with a total depth of 8 meters below the final platform level at its deepest point. This meant that the deepest base of the inlet works was merely at a 4 meters above mean sea level. This was about 6 meters under the water table. This was a major challenge during construction and meant 24/7 dewatering was required to enable contractors to work within the water table. Dewatering was achieved by creating rings of boreholes at depths of 4 meters plus at 1 meter center to centers. These boreholes were connected to diesel pumps, which ran day and night to ensure the water table was pumped down to create a dry working platform. In the next photos, we will show you the completed inlet works. The first photo shows you the 4 Archimedes screws that lifts the water into the rest of the inlet works. These screws are massive, standing at a total of 16 meters and 2 meters in diameter and 16 meters in length. It was quite a sight to behold the installation of these screws, as each screw required 2 cranes to lift it carefully into place. The following photo, you can see in the back, you can see the inlet work structure, roof sheltering the screens, and in the front you can see the 2 degritter rooms where the grit is cleaned and stored for safe off-site disposal. Okay, let's move on to the next step of the process, the primary treatment. So the decision to incorporate primary settling tanks, known as PSTs, into the system was due to the urgent need for treatment capacity in the activated sludge plants. PSTs provide a reduction in the influent organics, solids, and nutrient loads to the activated sludge plant at a cost-effective rate. This is done when comparing the additional capacity the PSTs can deliver versus the capital cost it costs to construct them. The screened and degritted flow from the inlet works is lifted by the upper screw pump station and distributed to the 4 primary settling tanks, which you can see in the photo on the slide. PSTs remove the settleable solids by means of sedimentation. The PST's underflow is discharged to the primary sludge holding tank at the sludge dewatering facility. The overflow from the PSTs, known as the settled wastewater, is distributed between the biological treatment plants, MBR-A and B, and the remainder is fed by gravity to the 2 CAS plants.
So the next step in the treatment is the secondary treatment. And on Zandvliet, we have 2 types, the membrane plants and the conventional treatment plants. So I'll take you through the membrane plant first. So Zutari was contracted to design a new 18 megaliters per day membrane plant. In recent years, membrane treatment technology has become one of the preferred methods for treating water and wastewater in many countries. The conventional treatment system, which separates solids and liquids through sedimentation, generally requires a much bigger footprint with lots of civil works involved. Skilled operator attention is also very intensive to ensure effective treatment. Whereas with membrane technology, although the capital cost is significantly more, the footprint required is much smaller, and it does not require many skilled operators, as most of the operation is automated. Another benefit is that with membrane technology, there's an actual physical barrier that separates the treated water and nutrients. So no matter what the inflow is like on the day, the quality of the treated effluent remains the same. So in the photo on the right, you can see this is what a membrane cassette looks like. It has thousands of these strands that looks like noodles. The wastewater sits on the outside of these cassettes and pumps suck the water through these strands. Each strand has lots of tiny holes with pore sizes that are 0.1 nanometers. So if you think of it like a straw, with thousands of these tiny holes, the liquid gets sucked through and the solids remain behind. So the newly constructed membrane plant was finished in 2021 and commissioned earlier this year. It is currently the biggest operational membrane plant in Africa. So the settled wastewater from the primary settling tanks is mechanically screened again before being directed to the membrane bioreactors. The bioreactor operates under a UCT type process with an ultrafiltration membrane plant attached to remove biodegradable organics, nitrogen, and phosphate from the wastewater. The cleaned water is then used as site service water, and then the sludge is stored in holding tanks to be dewatered. In this photo, you can see the ultrafiltration membrane plants. The cassettes are submerged under the grids. This makes the whole process area very clean. Each lane is equipped with automated valves so that the optimal cleaning sequence can be achieved. As this plant is fully automated, if there is an issue, you could turn on or off a specific operation in the control room on site or through your phone. So before the upgrade, we also had an existing membrane plant on site that was commissioned in 2009. This membrane bioreactor was a glass-infused steel round tank that treated an average dry weather flow of 18 megaliters per day. The tank outer wall itself was showing signs of failure. There was little leaks everywhere, and the steel wall bowed out at the bottom of the tank as well. The lifespan of any membrane cassettes is around 10 to 15 years, which means that they would have reached the end of their life expectancy. The reactor was also overloaded, so it had to be refurbished. The refurbishment process started by us pumping out and cleaning the structure. The steel walls were demolished and replaced with concrete walls as it lasts longer. We also wanted to retain as much of the existing footing as possible, which saved time and cost to the project, so that the inner wall base was not demolished. This meant that the new wall built is actually not tied to the existing footing and therefore does not transfer any moment onto the base. So the inner wall sits on a bearing pad that allows movement by a maximum of 6 millimeters in either direction to accommodate for the difference in water level of the different treatment zones. Construction is currently going well and on program, and it is expected to finish at the end of this year.
Okay, then I'll move on to the two existing CAS plants. The two CAS plants with an average dry weather flow capacity of 27 megaliters a day, respectively, was, as previously mentioned, constructed in 1989. Since then, the reactors have not been refurbished or upgraded. As part of the civil project, the civil contractors was responsible for the cleaning out of these reactors. Zandvliet is situated next to a major sand mine, and the southeaster wind almost blows on a daily basis across site. This has resulted in almost all existing structures being filled with wind-blown sand. Over the last 30 years, the sand-blown salts have settled to the bottom of the reactors, which has decreased the treatment capacity by almost 70%. In the photo shown, you can see the accumulated sand of 4 meters in depth after we emptied the first CAS. So we could only empty these CAS because after the construction of the new MBRB was completed, we had enough capacity on the plant to take one entire CAS plant and its related SSTs off at a time to allow us enough time to get into these CAS reactors to clean them out. After cleaning out, the mechanical contractor will be responsible for the refurbishment of all the mechanical equipment. This is something that we are currently busy with on site. I think those pictures are probably a week or two ago. This is a very messy job, as can be seen, but it is required to return the plant to its full treatment capacity. And it's not often that a plant has the luxury of taking, I think we are one of the first plants ever that can take an entire reactor offline like this, because we have enough capacity because of the completed reactor. So given the poor settleability of sludge observed at the existing SSTs, it was recommended that additional settling capacity is needed. It was therefore proposed that the upgrades provide for an additional 2 SSTs per cash plant to achieve effective separation between the activated sludge and the treated effluent. As can be seen in the left video, it was a very proud moment for everyone on site. It was where the first initial flow entered into our first completed SST. The video on the right is an even prouder moment. That indicates the excellent effluent quality from this SSTs weeks later. That is a SST that is fully functioning, and how the effluent should look from SSTs. The treated effluent from all 12 SSTs then flow through three chlorine contact tanks, where it gets dosed with chlorine gas to remove the remaining pathogens. Thereafter, the water is safe to discharge into the Kales River and into the environment.
So the last step of the treatment process is solids treatment. During the design phase, we looked at different technologies for sludge handling, and 2 prominent ones were considered, being the centrifuge or the bow press. Our studies looked at the total footprint required, maintenance during the lifespan, the net energy used, the amount of chemicals needed, the capital and operational costs. We found that although the centrifuge required a much smaller footprint, they require significantly higher capital and operating costs, as well as higher energy demand and chemical consumption, making it very expensive overall. Therefore, we went with the bow presses. Before construction, we modeled the civil infrastructure as well as all mechanical equipment using the software Rivet, and utilized VR technology to check for any clashes. We also invited the client and key operational staff to give their input on improving the ease of operation and maintenance. So on Zandvliet, dedicated bow presses were needed to treat the two different kinds of sludge, as primary sludge is a lot thicker than waste-activated sludge. From the primary sludge holding tanks, the sludge is pumped into 4 primary sludge bow presses. The WAS is then pumped from the WAS holding tanks onto linear screens, where the sludge is thickened before being dewatered through the belts. The dewatered sludge from all the bow presses is pumped into their respective silos and transported either to landfills or used as fertilizers on farmlands. Most of the equipment we have on site are actually from overseas, and the bow presses were from Germany. And I was extremely fortunate to be able to go to the factory in Germany to inspect the machines before they were shipped to site. So there are actually a lot of travel perks that comes with this work.
Okay, then I'll move on to the administrative building. I was extremely fortunate to be sent to Zandvliet for the administrative building. Okay, so the purpose of the administration and control building was to provide a considered, robust, operator-centric facility and office space for the end users and the visitors to the Zandvliet wastewater treatment works through a simple yet bespoke architectural intervention. The building size is approximately 2,100 square meters, which includes the ground floor, first floor, and carports. The construction period commenced in October 2019, and the client, the City of Cape Town, and the plant operator, Water and Sanitation South Africa, took occupation of the building in August 2021. This is the only building on Zandvliet where we had architects involved, as you can clearly see from the aesthetical appearance of this building. On your screens, you can currently see the architectural design render pictures of the building before construction commenced. Keep these pictures in mind as I will be showing you the final construction pictures next. The building has functional areas such as administration offices, operator locker rooms, canteen spaces, laboratory with chemical stores, laundry facilities, multi-purpose training facilities, ablution facilities, medical bays, a braai facility, and then last but not least, probably the most important, the operator, server, and control rooms where the entire plant can be operated and managed from on a SCADA system. The laboratory is also where the final effluent gets tested on a monthly basis to ensure the plant effluent complies with national effluent standards. So the building currently complements 16 process and 8 administrative staff with a possible future space for 38 more staff. The spaces inside the admin building were designed with the philosophy to be transparent and democratic, which enhances the interaction between users and operators inside the building. The building has a glass facade towards the plant that allows all operators to have constant supervision over plant operations. The building was also constructed with robust, low toxic, and low maintenance materials. The following pictures are some of the photos taken during the construction phase of the admin building. Construction of this building taught myself a lot of lessons in particular. Firstly, dealing directly with architects, so on a daily basis, basically. So having a specific level of detail and quality in mind at all times can be difficult. It can be difficult to find that middle ground between the architect's dream and the engineer's solution. But it also taught me a lot about building regulations and including health and safety and fire requirements in all designs. At the end, it came out quite beautifully. And I think it's something that both us and the client can be proud of. A state-of-the-art building and a space where you would want to work in.
So as for the future, it is bright for Zandvliet. There are big plans in the works, the first being the water reuse. So during the droughts that devastated the country, the City of Cape Town, in its water strategy, has identified, along with water saving and demand management, the need to diversify their sources of drinking water. This will allow for a more resilient water supply. They have committed to source an additional 300 megaliters per day of drinking water from non-surface water sources by 2030, which will include desalination, groundwater abstraction, and water reuse. Zandvliet has been identified as one of the most promising wastewater treatment works from which to draw wastewater for water reuse. Space has been allowed on site for tertiary treatment facility to use the cleaned water from the membrane plants to feed an advanced water purification plants off-site. Another future possibility is energy recovery. During the sludge handling workshops with the client, it was understood that this was something that they were interested in for the future. It is possible for sludge to be digested anaerobically, resulting in a methane-rich biogas, which can then be burnt to generate electricity and heat. This would either be treated on site at Zandvliet or other facilities in Cape Town. Provisions to treat on site has been allowed for in our design. And as you know, we have been experiencing a lot of load shedding recently. Zandvliet is very hectic in energy consumption. During load shedding, enormous amounts of diesel is consumed, and this comes at a very high cost. If it's not pressing then, it is certainly more relevant now. And hopefully some of you will be working on these projects in the future. So to conclude our presentation, we'll be sharing with you some lessons we picked up along the way. So Zandvliet was not a greenfield when we took over. Therefore, trying to place every new structure in a sensible way was not an easy task. For example, the original designers of the conventional activated treatment plant envisaged a total of 12 secondary settling tanks to be placed in the way shown on the screen. However, when the first MBR was constructed, and because of the space limitations at the time, it was placed where the future settling tanks was to be built. This forced us to find alternative space for the new settling tanks. And because of the new positions, channels instead of pipes have to be designed to get the wastewater to these tanks. Designing on a brownfield comes with various challenges, but if you just apply your mind and think it through, you can always come up with a smart, innovative solution. Another thing is, when designing, always keep your end users in mind. Think how will the design work for them? How will they get access to a certain equipment so they can maintain and operate? The more user-friendly, the better. For example, on this contract, we installed these valves in a chamber that is 1 meter off the ground. However, what we didn't account for was that the valve spindle sat another meter above the chamber. So now the operators have to get up on top of the chamber to open and close the valve, which is unsafe and inconvenient. And we are resolving this on site. When producing any construction drawings, it is always good practice to keep the contractor and the builders in mind. Think which annotations and dimensions will better help them understand a structure to build it correctly. Always show a plan of the structure and include key sections that shows the complexity of the structure. Lastly, one of the biggest lessons we have learned is that if you're not familiar with something or don't understand how to design it properly, always consult someone who has worked in that field. Use your colleagues and teammates as sources of information in areas where your skills are lacking. Also, the more you ask, the more you learn. I am a civil engineer that designs buildings and services, but along the way, I have learned how to size and select pumps for specific processes. So never be afraid to ask, and you might just pick some extra skills along the way that make you become a better, more well-rounded engineer.
Okay, then so construction lessons. The various lessons were learned during the construction phase of this project. A lot of them have been mentioned and shown in the previous slides. Some of the ones not yet mentioned, for example, is the sequencing of the works between all 4 contracts. As mentioned previously on Zandvliet, there were 4 contracts running concurrently, 2 mechanical and 2 civil projects. This is a very difficult one to manage at a construction phase if this has not been done properly, if this has not been thought through properly from the design phase. Luckily, our design team at Zutari did an excellent job designing and setting up the contract documentation in such a way to allow the correct sequencing of all contracts within the works without any delays or claims. If not done correctly, this could lead to heavy penalties and delays on either of the contracts. Okay, then adhering to the program and project timeline. This one is quite obvious, but also worth mentioning. This is crucial on all 4 contracts. Falling outside of program or project timeline can lead to major penalties. This can be prevented by constantly revising and revisiting programs to check on the contractor's progress, allowing more resources when you see the contractor falling behind on critical path items to ensure the project never falls behind. Currently, all 4 contracts are on program. The first civil contract finished comfortably within program with a few months to spare. This is thanks to excellent management by the relevant Zutari teams and great teamwork with well-rounded professional contractors. Then staying within budget. Staying within budget sounds easier said than done. On Zandvliet, the scope of the project changes on a monthly basis. For example, items like the cleaning out of the CAS plants, the cleaning out of MBRA, the entire scope of MBRA changed. We're currently planning to build a new MV substation to feed the site. All of this was not in the original tender or drawings. So therefore, staying within the budget while completing all scoped works, as well as the additional works of the wish list of the client added on during the construction phase, is difficult, but it is achievable with proper cost estimates, monthly budget discussions, even weekly, and finishing final measurements of structures as soon as the structures get completed. Then on existing services, as the latest Zandvliet projects on a brownfield site, as previously mentioned, the amount of existing services was truly terrifying. Working in and amongst existing pipes, cables, electricals, optic fibers, and other services was a big risk. Damage to electrical could lead to the entire plant going offline and flooding of all structures. Damage to existing pipes led to floods. Both of these incidents happened on various occasions, as the as-built drawings from the 1989s was not as accurate as it is today. To prevent these risks, all new services and exposed existing services was accurately surveyed and recorded and indicated clearly on as-built drawings for future projects to know exactly where all services are in all areas. In areas where future works was expected, especially electrical and fiber optic cables, was placed in ducts to prevent possible damage. Site safety is, as everyone knows, that's a very big one. All activities on site had to abide by the Occupational Health and Safety Act, Act 85, the OSH Act 85 of 1993, and the Client Health and Safety Specifications. This is enforced on a daily basis by us, the engineering team, the contractor, and the operational health and safety agent on duty. An external health and safety audit was conducted on a monthly basis to ensure compliance. Some of the major operational health and safety activities done on site are, but not limited to, deep excavation practices, working in confined spaces, working with pipelines, within pipelines and manholes, working at heights, working in and amongst and in close proximity to hazardous material. So all the necessary training, inductions, and inoculations was required to be done by all parties before entering the site area. Daily visitors must receive a daily induction before accessing the plant. Then lastly, the environmental on the final effluent. This type of project has a major positive impact on the surrounding communities. Not only does it provide a well-designed and functioning sewer network to the informal settlements and to most of the households, but it also cleans the sewer and puts clear, clean water back into the Kells River that flows through our communities. So to finish off the construction lessons, we we encountered a lot of unexpected issues on site, such as floodings and vast extension of scopes. But this was all well managed within the team and with the contractor, and I think it's been a valuable experience to everyone involved. Yeah, then thanks everyone. That concludes our presentation. Just a side note that the above structures are only the main process structures on Zandvliet. There are a lot of smaller structures which we have completed in the last 5 years that also play a very important role in the process, which was not mentioned. Thanks, everyone.
Right, thank you, Vicky and Ben, and I think they deserve a round of applause from those of you in tonight's session. Before we lambaste them with the questions that have been raised, and it's pity your EXA registration wasn't as easy as that. Okay, let me just go through the questions in the chat to start with, and if you do want to ask questions directly of Vicky and Ben, they are presenting from the same workspace, so they will decide amongst themselves who's going to handle the questions. But let's start with the first ones from Motsepi. It says, according to you presenters, so that Vicky and Ben is you, how will the problem of climate change affect water quality in the coming years? And there's a second part to the question, and also what can environmental water engineers do, or what role will they play, and to what significance in tackling this problem? That sounds more like an examination question.
I know, we are stressing here.
So let's start with the first part. How will the problem of climate change affect water quality in the coming years?
I'm really not sure about that, but we designed the wastewater treatment work based on the flows and loads, so the incoming nutrients that we receive. So we build structures accordingly to treat those flows and loads. So so far, climate change, I don't think has affected us, but I am really not sure.
So, yeah, what you're saying is the plant's estimated designs were done for projections of what the plant would need to treat in 2030, which was 150. So, for the plant to be able to treat 150 megaliters a day, the civil infrastructure is in place. It would only need additional mechanical upgrade.
Yeah, so
Okay.
in case like if climate change goes into the way of massive rains that were expected, that were Durban experience, then there is, like I said, redundancies built into the structure at the moment to accommodate a higher flow.
But if the climate change goes the other way, then we won't have potable water so we'll get no sewer on Zandvliet, basically.
Okay, well dodged that one. Next one was, what can environmental and water engineers do, or what role can they play in tackling this problem? So you've sort of answered that already. I don't know if you want to elaborate a bit further, either in design or construction considerations.
So I think they should obviously closely monitor the quality of the effluent, and we should actually get these upgrades sooner rather than later, because when we took over this upgrade, the flows coming in were already exceeding the upgrade capacity.
Okay, so it's not designing and upgrading just in time, it's having the foresight to make sure you've planned well in advance.
Exactly.
Not that that's an easy one to sell to the client, but that's the optimal approach.
Yes, yes.
Okay, then the next question is from Tabo. He wants to know, and this, Ben, I think related to your video of that concealed pipeline or whatever it was. How did you solve that flooding problem? I know you had to pump all the liquid out, but what did you do to stop it happening again?
Yeah, so firstly, we obviously pumped everything out, and then we had to run the dewatering again to get the surface dry, and then we blocked up the opening by
Yes. So it didn't actually happen under our contract, so we're not 100% sure. But I think they waited until low flow, like low enough, so the water went down a bit, and then they blocked it from the outside, then they pumped the water from the inner chamber out to be low enough for someone to go in and close the sluice gates. Thereafter, we just pumped the water out from the outside and then blocked it permanently.
Luckily, it was not an opening, but more a sluice gate that was left open. So there was an actual sluice gate to block the opening. It just needed to be closed because it was always submerged.
Okay, and then there's a follow-up question from Tabo, and he said, and what were the environmental impact implications of that event?
So the surrounding soil was obviously contaminated with the sewer incoming water, but luckily this material was being excavated and removed to get to the new bottom of base level. So this material was excavated and then safely removed from site.
Okay, the next question is from Olerato. The question is, what impacts, if any, did the construction of the wastewater treatment plant have on the surrounding communities, and in which ways were these impacts addressed?
So I think it had a positive impact on the surrounding communities as it hugely improved the quality of the effluent water. In other ways, it also created job opportunities for the surrounding communities as we had to also hire local labor to a certain percentage.
Yeah, at our peak season, just our like in the first year or two, just our civil contractor employed about 150 local labor on top of the 250 labor team they had. That's just on our civil contract, and on the other civil contract they basically almost had the same. So in terms of jobs creation, it had a major impact, and in terms of all of these labor were also trained on the job and given certificates. And in terms of the environmental impact, I think the Kales River is much happier and much cleaner today than it was 5 years ago.
Okay, and then the next question is from Bongani. He asked, now that the plant has been commissioned, how is the impact of sand blown towards the plant dealt with? Does it not affect the plant now, and how do you plan to deal with this in future projects if the site conditions are more or less the same? So I think that was your desilting, whatever you called that acronym thing, Ben.
Yes. So it's a major issue currently because some of these structures have been left for 15 to 30 years. So our long-term plan is to not have all the areas in between the structures as sand. We are planning to grass and pave most of them. But obviously now, while construction is busy, as you saw on the Google Earth photo, most of the areas are just sand. So it's because it's driven over and there's no real time for the grass to grow. So as soon as construction starts calming down, then we will be focusing on the landscaping and the grassing and thereby controlling the dust. We have been thinking of installing like dust barriers on the southern side of site where the southeaster comes from. So that's also still in discussion.
Yes, and I heard that in European countries, they've already implemented covers on all the CAS plants. So hopefully, if we ever build a new one, we'll also have covers.
Okay, and then I'm not sure if you'll better answer this question, but here goes. It's from Mohammed. He says, out of interest, what is the actual plant electrical load? You indicated Vicky, that the expensive diesel when you've got load shedding, what is the energy requirements of the plant?
I don't think we are the correct civil engineers to ask. We're not
No.
that electrically inclined.
Mohammed, you must
Well, I
understand.
think the civil engineers would do a better job of making the electricals work than the electricians at the moment.
True.
Okay, so
I wouldn't know the exact
Number, but
like
it's very
numerical
high.
value to it.
okay, and then the last question in the chat is from Panache. He or she says, how did you tie in compliance matters into your planning program? That is the water use licensing application, to be specific. Where did you place this on your planning program?
Oh, this is a difficult one.
There had to be one, eh?
Yeah, I think that might have been one of the activities. Me and Vicky was not part of the team. So before we were sent to Zandvliet for the 3 years as engineers representatives, that would have happened, and I don't think we were part of those teams. Do you know, Vicky?
No, I have no idea, but maybe, I don't know, like the compliance matters into your planning program, maybe that's penalties? I have no idea.
Okay. Okay, I'm going to go and just check to see if there's anybody that would like to ask a question from the floor, from the audience. Just raise your hand and I will unmute you so that you can raise your question. We are a little bit shy of our time. They did such a good job of running through it. I'm still waiting for the deep end. I'm not sure what that was, but looks to me like it was bun and coke, this job. But then I'm a putt marker. What do I know about wastewater treatment works?
We don't want to scare anyone off civil engineering.
Okay, true. Yeah, they may change courses.
Exactly.
Any questions from the floor before we let Vicky and Ben go and enjoy the food that they both said they like to eat in Cape Town? Don't be shy. I know there are lots of the Zutari colleagues in the audience. If you want to make their life even more difficult, you can ask even more challenging questions than the electrical one.
I know where they sit.
It looks like you have done such a good job that there are no questions.
Okay, so someone asked, what is the life expectancy of a reinforced concrete water treatment tank compared to the steel tank? So the steel tank was constructed and commissioned in 2009, so it was approximately 13 years ago, and it was already showing signs of failure. Whereas a concrete tank, I don't know, it can go 50, 100 years. Like we just emptied out the cast tank now, and it was commissioned in 1989, and the concrete still look good. Yeah. So it's much, much longer.
And the quality of concrete and the amount of steel that is used nowadays compared to back then has vastly increased. So yeah, I don't think you can. It's a very long time. It won't be in our lives that the concrete structures.
The second part of his question was, which of the two materials would you recommend?
So definitely concrete, yeah.
100%.
Are you biased, or is that because it's the best solution?
Just concrete never fails.
I'm sure there will be many that will argue that point, but I accept your logic. And then there is another observation here from Tabo. Ben, this is particularly for you. He says he thinks you and him were in the same 2019 at Seaput group with Mr. Patrick Neal and Mr. Sutherland on the dissertation. So you have a classmate in the audience tonight.
Oh, fancy meeting you here, Tabo.
Yeah, you need to keep in touch with your university buddies, you know. Anyway, I don't see any more hands. Lots of compliments in terms of the audience for your presentation. And thank you to Jeff for volunteering you as the victims. That concludes our session for today. And obviously the recording will get put up onto SAICE's YouTube video at some stage. We'll just edit out the beginning and the end so you don't have to listen to too much BGs. But Vicky and Ben, thank you very much for a very, very interesting presentation. Like I said, as a potmarker, I even learnt a few things. I'll have to go and look up all the acronyms you were rattling off, but I'm sure the people that are involved in the wastewater environment would have understood what all those things mean. You are getting a sitting virtually standing ovation. So thank you both very much, and good luck with the rest of the year and the project. And maybe we can touch sides with you again when it is finally finished and see what it turned out like. I see there's a hand, so let me just go and, oh, it's gone. Rosanna, don't be shy. Where's your hand gone?
I think he was trying to clap hands.
Oh, okay. Never mind. We accept that as being a clap hands. So if you want to escape before somebody does raise a hand, then thank you very much, Vicky and Ben, and good night, everybody. We'll see you again for the next one. Last Thursday of next month will be a presentation by what was KV3 Consulting Engineers, whatever they call themselves now. And hopefully we will get you information on that in the next week or so. But Ben and Vicky, thank you very much again for the effort and for your time. And as I said, good luck with the rest of the project. And on behalf of SAICE Academy and SAICE SAS, thank you for enlightening our students and making sure that you didn't frighten them completely away from going into civil engineering. Thanks, everybody. Okay, cool. Take care, everybody. Cheers.